This episode is brought to you by Audible. We often discuss colonizing planets around distant alien suns, or building artificial habitats around our own sun, but building suns might be a stellar idea. We spent a lot of time talking about making artificial habitats or entire worlds for humanity to live on in the future, and I thought it was past time we talked about the suns that would light them and how we can go about making those. Now, a point we often make about megastructures and artificial planets is that they hold three critical advantages over planets. First, they use vastly less mass and material than a planet does for the same total living area, because for the most part, there's no need to have your ground go more than several meters deep, rather than several thousand kilometers like on a planet. You can get 1,000,000 times the living area out of a planet by turning it into tons of rotating habitats rather than a big sphere, or by using something vastly more abundant than rocks and metals to fill that sphere, like compressed hydrogen or helium, or black holes made of those, or maybe even dark matter. Second, you can build them wherever you want, and to a customizable size and gravity. There's only a fairly narrow window of both location and composition that's going to produce a planet people can reasonably make habitable and Earth-like. And third, you can get very exact with replicating certain Earth-like conditions on a megastructure. It would be almost impossible to find a planet with an exactly 1g surface gravity, 24-hour day, and 365-day year without blowing huge amounts of energy trucking in or removing mass, altering rotational and orbital rates, and so on. But when we build them ourselves, we can tailor gravity, day, and year length very easily. So we use the analogy of comparing planets to mountains with caves in them. A primitive civilization hunts for good caves on a mountain. A more advanced one just quarries rock and builds its own caves wherever it pleases, and can make a lot more artificial caves or houses out of a mountain than it will naturally have. Instead of maybe half a dozen caves on one, you can cover a whole continent in millions of tailor-made homes instead. This is our basic concept for habitation megastructures. However, you can't really put these wherever you want. You're still fairly limited to where the sun shines comfortably, its habitable or Goldilocks zone, not too hot, not too cold. We can expand that a lot by using solar shades to block some sunlight where it's too hot, and mirrors to add sunlight where it's too cold. But while this immensely expands your zone, it's still tiny compared to space. It would be quite challenging and resource-intensive to keep a planet warm by sunlight all the way out at Neptune or Pluto, as light falls off in strength by inverse square of distance and is 1,000 times weaker there. This starts us thinking about why we might want to make an artificial sun, and while we start with basically the same logic and reasoning as with megastructures, in fact it's actually worse. Planets have a very narrow range of habitable sizes, especially if you're looking for close analogs to Earth, but stars are even worse. You could probably terraform a planet fairly easily that was 1/10 heavier or lighter than Earth, since composition affects density, which affects surface gravity, but if that density is pretty similar, and it often is, surface gravity is proportional to radius, 10% wider, 10% more gravity, but 33% more volume and thus mass. One only 10% more massive of the same density would only be 3.2% wider and have 3.2% more gravity. One with 90% of our mass would have 96.6% of our normal gravity. Based on how heavy you felt, you'd have a hard time noticing you weren't on Earth on either planet, but stars are a lot more sensitive about mass. Composition matters for them too. They're not entirely hydrogen, and not all the remainder is helium either, but as a loose rule of thumb, star lifetime and brightness are directly related to mass. Even a 10% increase in mass is increasing a star's brightness by 40%. That means its habitable zone just moved 18% further away, and orbital periods are much less sensitive to mass, so even with this minor change of mass, you aren't getting any 365-day years in your habitable zone, at least not without artificially extending your day. On the extremes of this, around the smallest of stars, you have planets whose year is measured in days, as is its day since it will probably be tidally locked that close to its sun. On the more massive end, where luminosity can be 1,000,000 times brighter than our own sun, even though the star is maybe only 20 or 30 times more massive than our sun, your habitable zone is so far off your years might take thousands of Earth years, and your star would be so short-lived you'd barely have time to get your civilization going before it blew up. This extreme highlights a third issue too, which is how wasteful sunlight is. Our planet absorbs less than 1/1000th of the sunlight emitted, around those big ones that would be 1/quadrillionth. That's the whole reason why we like the concept of a Dyson swarm, because a planet's civilization isn't like a tribe sitting around a campfire to warm itself at nights. It's like a tribe living next to a forest fire to stay warm. It's very wasteful because stars are omnidirectional in their emissions. That's not as bad with the cooler and dimmer stars, where a habitable zone planet might be getting thousands rather than billions of the light released. But for those giant suns, it's ludicrously wasteful, and they're so short-lived, there's not much point to trying to englobe them to tap that power before they explode. So we're interested in artificial suns today, and we might as well start off with the conceptually simplest method, which is to mimic nature. This has limited customization options, but at least has some, since we at least get to pick location. Let's review the natural method of star formation then, since we'll basically mimic it, and it often begins when big stars go boom. The galaxy may contain a lot of stars, but most of the galaxy's mass is not in stars, even ignoring that most of it is dark matter, which will be of interest to us later today. Only a fraction of the ordinary matter in the galaxy is bound up in existing stars, including dead degenerate ones like white dwarfs, neutron stars, and black holes. Most is floating around in giant clouds, and left to its own devices, those would all slowly clump up and form stars. But they often get an assist when a star goes supernova, and the shockwave perturbs that cloud and sets off a lot of matter clumping up and forming stars. Usually a large pack of them will be born about the same time and move around the galaxy together as a small cluster, something that is very handy for astronomers. Many other things can prod stellar formation, like a cluster of stars passing through a cloud of gas or a galaxy eating a neighboring galaxy, which has happened a lot down the eons. Typically a dense cloud of gas is what we call a nebula, which are where many stars form, though that's a fairly hazy term. The first nebulae we saw were essentially hazy dense clouds lit by lots of new stars. In terms of astronomical timelines, this process is fairly fast, but still takes millions of years. It would not be too tricky to guide this process to arrange the new stars to be at the sizes and locations of your choosing, and even speed it up a bit, but we probably want to go a lot faster. As to how fast this process can go, that's really a question of how much brute force you're willing and able to expend. There's nothing stopping you from building freighter after freighter to just gather up hydrogen and dump it at some spot of your choosing. You could also build huge quantities of ultra-thin panels in a huge sphere that you gave a shove with light beams, so they pushed gas along the way to eventually collide at the place of your choosing. Emphasis on ultra-thin, because the interstellar medium is so low density that you need to sweep out a volume on an order of a light year across to get enough mass for a star. That is, after all, why they tend to be several light years apart from each other. Such a big shell, even when thin, would be very massive. You wouldn't likely do this direct scooping approach in favor of pushing gas with light or magnetic fields, but it illustrates the basic concept. Similarly, we have the option of moving failed stars, like brown dwarfs or superjupiters, so as to collide with each other to gain enough mass, which saves you a lot of the work and effort of collecting your own mass, though you still have to shove them together, which is no small feat. Before we proceed though, I just want to emphasize that as huge as the energies are, when you're talking about shoving gas giants and brown dwarfs around, it's still tiny compared to what a star will give off. Shoving a planet up to 1,000th of the speed of light, so it will collide with various others you found in the region a few thousand years later, requires the kind of energies only available to K2 civilizations. But that's not a catch-22, since any given civilization already has at least one star to become K2 around in the first place. You're also not shoving them too fast because you don't want them colliding at speeds higher than their own escape velocity, or they'll just explode and blow your mass all over the place, with most escaping rather than falling back together. This saves you on energy, but not on time. Again though, it is a lot of energy because it is a lot of mass. Making Jupiter into a second binary sun is a popular idea in fiction, but it's nowhere near heavy enough to become a star on its own. The universe is pretty old though, and has a fair number of big dead stars lying around, and some could be rekindled by dumping a gas giant onto them, not for long in astronomical terms, but quite long in human civilization terms, so some might opt to do this. You'd have to do it very carefully though, feeding gas in small amounts to that star, not in big chunks, since that's basically what causes supernovae to occur. The old big star blowing up, what most folks think of as a supernova, is a Type 2 supernova. Type 1 is when an old white dwarf star absorbs enough new mass to light off. Type 2 are thought to be a bit more common, but are less bright than Type 1. That is something to keep in mind when thinking about stellar engineering with degenerate stars. Oops is not something you want to hear from your chief engineer, as moments later you'll both be getting your atoms scattered by an explosion bright enough to outshine the whole galaxy for a while. Of course, as we mentioned, supernova shockwaves are often what causes the formation of stars, and also release the heavier matter we need for planets. So intentionally detonating some white dwarfs by slamming a brown dwarf or Jovian planet into them might be a very low-cost method of making a lot of stars, especially since you could be pre-positioning other brown dwarfs or Jovians in places you'd like your new stars so they can act as clumping agents they'd form around. So that's one way to make a large gas giant into a star, feed it into an existing one. However, brown dwarfs already fuse deuterium, the easiest hydrogen isotope to cause fusion, and if we're making artificial suns, we can also control composition. With naturally occurring stars, you'd have a very fixed set of parameters for its mass, lifetime, size, and luminosity. You can't find a star the mass of our sun but twice as bright, or half as bright, because they're all made of pretty much the same thing. They all begin as mostly regular hydrogen, with a decent amount of helium and deuterium in them, and many of the younger suns also have a ton of heavier metals in them too, what we call population 1 stars like our own sun, ones with a higher metallicity. Metals in this case referring to elements heavier than hydrogen and helium. Metallicity increases with each generation of star formation. This is still a pretty small fraction, usually around 1% or 2 even in high metallicity population 1 stars. But irritatingly, that still means there is more gold and other valuable metals in our sun than in the rest of our solar system combined. It's just very hard to get at it. And if you're curious on how we could do this, see the star lifting episode. But most of that non-hydrogen is helium, and you could get more as stars age and transmute that hydrogen into helium. In many stars, this slowly poisons them till they turn into red giant or Type 2 supernova, long before they use up all their fuel. But in the smallest stars, this will never happen, instead resulting in what we call a blue dwarf, a smaller red dwarf who has burned up most of its fuel but does not expand into a red giant, though it grows hotter and more luminous. Or I should say what we will call a blue dwarf, as none exist yet because the universe is quite young and all the stars small enough to become blue dwarfs won't for many hundreds of billions of years to come. If they're natural ones anyway. nothing is stopping us from making a star that's half hydrogen and half helium, burning brighter than it should for its mass, and still living much longer than our own sun would, even though it could be set to the same temperature and spectra as our sun. It would be much less massive and dimmer, though still brighter than a normal red dwarf of its mass, and that could be quite handy. Metallicity also plays a big role in star brightness and lifetime too. For instance, we have a third type of star, population 3, ultra low in metallicity, which are thought to have been the earliest stars, and it is believed that these could potentially get far bigger than modern stars because of their low metallicity. Normally a star can't get much more than a couple dozen times the mass of our own sun without hitting the limit for stellar mass, the Eddington limit. Star fusion rates climb very quickly with mass, so they get hot and try to expand, while gravity holds them together, and stars achieve a size based on hydrostatic equilibrium, where the pressure from the rate of fusion and gravity balance. Metallicity plays a big role in that since heavier elements won't fuse but still add gravity, pushing the star together to create faster rates of fusion. High metallicity stars are hotter, so are older stars which have more helium since that won't fuse normally either. In a basic main sequence star, if you get over a certain mass, the outer layers tend to blow off, limiting size. The population 3 stars of the early universe, super low on metals and helium, could get bigger, and could also die in black holes in a somewhat atypical fashion, via photodisintegration and a pale instability supernova. We'll bypass discussing how this happens, since it probably no longer happens today, just in the early universe. And if you'd like to know more about those stars, consider watching PBS Spacetime's episode Fate of the First Stars. But one interesting note, it's thought this type of stellar death results in a black hole and a supernova that shoots out as a pair of relativistic jets rather than big omnidirectional explosions. That's a pretty handy way to rapidly produce and capture a lot of heavy elements. So same as you might build stars intentionally heavy on helium or metals, or straight out of deuterium, you might build a star of pure hydrogen just to use it as a massive transmutation star forge. Or stellar cannon, since it comes out as a jet you can probably aim. But there are much easier and faster ways to obliterate planets, as we've discussed before. Those black holes are interesting to us though, because fundamentally, a star is just a convenient natural way to make a lot of light. It need not be done by fusion any more than the photons leaving your screen to let you watch this episode were made that way. The brightest things in this universe are quasars, or were quasars anyway. Like population 3 stars, they were much more common in the early days of the universe. That's the only reason we can't see them with the naked eye. They're almost all gone or weakened nowadays, so you'd have to look really far away in distance and time to find one. They are black holes, usually giant ones at the center of galaxies, active galactic nuclei, and the power they give off is from the accretion disks of mass falling into them and getting super hot as they collect. Indeed, without accretion disks, black holes, infamous in science fiction for sucking things in, would almost never suck anything in. They have no more gravity than the star that bore them, indeed a good deal less, and they are very small. An object passing by them would just be pulled into an orbit around it. There's a maximum to how eccentric such an orbit can be with a planet or a normal star, because if it's too eccentric, the orbiting body will just slam into it, or be roasted by its sunlight or atmosphere. And once it's in orbit, there's usually enough trace gas in the lower orbit to slowly deorbit an object so it falls down. A black hole accretion disk serves this role too, only much hotter as there's much more gravitational energy involved. Let me note though that this does not work on dark matter. It doesn't interact with anything but gravity, so it can fall right through planets and won't get random collisions in orbit to change its momentum. But it can't escape from a black hole if it actually intercepts that event horizon. but that would be a very rare event unless the black hole was moving rather fast relative to the local medium, so that the very small cross-section it has hits more material head-on. We currently have no way to manipulate dark matter beyond gravity, but we might figure one out someday. We've discussed using it as cheap filler mass for artificial planets, but you could also use it for stars. Gravity drives rates of fusion, and dark matter produces that normally. It also won't collide or pick up heat from sitting in a star, so if you've collected a lot of dark matter at some spot, and reduced its speed to less than the escape velocity of that spot, it's sort of like an artificial gravity field. You could use it to dope stars so they'd have different mass and brightness than normal. One way you could produce a 365-day year on a planet orbiting a star with a smaller habitable zone than our own sun, which is most stars. You can use this same trick to add gravity to smaller planets too. Getting back to black holes, without the accretion disk, it's virtually impossible to actually end up in a black hole. This wrecks many science fiction stories about accidentally encountering one because they are invisible till it's too late. You'd actually have to work very hard to fall into one that lacked a large accretion disk. But matter and gas slowly collect up around them and bang into each other and decay to fall in and speed up and so on until you get that disk, which is much bigger and which can intercept matter easier and trap it to eventually fall in, getting hotter and giving off a lot of light. And since this is outside the black hole's event horizon, that light can just wander off, if a little redshifted from leaving the gravity well. Needless to say, you can drop matter into a black hole in a controlled fashion to produce power, like slowly feeding it a gas giant. And if you wrap it in a substance good at absorbing gamma radiation and X-rays, and with a very high melting point, you can make yourself a colossal light bulb. Of course, there aren't a lot of black holes conveniently lying around. The stars that make them are quite uncommon, but again, that's relying on a natural process. There are a lot more neutron stars out there, and even more white dwarfs, and they could be pushed over the line into black holes, especially if you instead were feeding them something like iron, which is massive and useless as a fuel. But you need not use a star. If you have enough iron or something dense that won't fuse, you can just pile tons of it up till you get enough that it falls inside its own event horizon, but this would result in a very large black hole. So you'd probably make it a big dense object, then implode it by making a shell of hydrogen bombs or antimatter around it and detonating it. This should allow you to make one much smaller than the ones that naturally form, and you can now tap it for power by dumping mass down inside. Of course, we have the other option for even smaller black holes, which emit Hawking radiation at higher rates the smaller they are. Black holes in the megaton range are perfect for small stars, though you need to convert the light from gamma radiation to something safer. These can also be nigh impossible to feed, as they are smaller than atoms and also gushing out power. Another approach is to find a sweet spot for a modest-sized black hole whose Hawking radiation or accretion energy from dragging matter down is just powerful enough to heat a gas around it to push it away and only let a trickle fall in. That heated gas feeds the black hole and emits light like a normal sun, only much smaller and dimmer. This particular version wouldn't be too customizable, but should have a set size based on what gas you're feeding it, one that absorbs gamma and emits it as normal light. So you could customize a bit by using hydrogen and helium mixes instead of raw hydrogen or other gases, and this would let you play with your visible spectrum to match it to normal sunlight too. These would be quite massive compared to a Kugelblitz black hole, but still far smaller than a natural star. When you start going smaller, you can also play with day and year length more. We orbit stars, but we can make artificial stars orbit us, like in the geocentric model, and we can also put dishes around them to bounce light in the direction we want, so the supermajority of it isn't wasting itself into the void. For simplicity, we would call these sun moons, where they orbit a planet. They can be many things: big dishes reflecting a beam of light from a star farther off, a giant light bulb powered by fusion, a black hole, and so on. Now, if you're going the straight Kugelblitz black hole and Hawking radiation approach, you probably aren't using a single one for a single planet, but likely a small swarm of them orbiting each other fairly tightly, but not so tight they'd be able to merge. They don't have much gravity though, and you can push them. Pushing black holes is simple enough, just don't use anything you're attached to since you won't get it back. Using many small ones lets you add their power. Again, the more massive a black hole, the less Hawking radiation it gives off, but the longer it lives and the easier it is to feed or push on. You have to push harder to move it, but the small ones are so small you'd have problems hitting them. It's hard to aim a pushing laser at something smaller than an atom that's giving off huge amounts of radiation. Using multiple ones to form a single artificial sun opens up the door for some alternatives. First, we aren't necessarily bound to make one spherical sun anymore. We can string them together as needed, which is handy for a lot of habitats which are cylinders or rings. And you can do this with light bulbs powered by electricity or mirrors which are shaped appropriately too. But I wanted to finish out here because it's kind of the ultimate upgrade for making your own stars, be they classic stars you just made or functioning on different principles. We always talk about making Dyson spheres, or rather Dyson swarms, around a star to get all of its power, tons of objects orbiting that star. And we've talked about moving stars and today about making them. But you could make a Dyson swarm of stars themselves, moving them to near your own system or building them there. We often say red dwarfs are the most efficient of stars. The smaller ones use up all of their hydrogen and even the bigger ones most of it. And you could create a very large swarm of stars of a mass and brightness of your choosing to make a super solar system or mega Dyson. Or a more loose cluster where each star was far enough away that its light didn't impact its neighbors much, but still far closer than neighboring stars. Lots of bunched together little solar systems. For our own sun to be only as bright as the full moon is on Earth, it would have to be a bit over 600 times further away from us than it is now. But that's only a few light days away, not light years, and a fully convective red dwarf could be about 10 times closer, mere light hours away, only a little further than our outermost planets. You could go smaller and closer too, but dimmer and cooler stars also waste more of their light in the infrared range, so as massive as you can go and still be fully convective, around a quarter of our sun's mass, is probably preferable. They're only 1% as bright as the sun, but that just moves your habitable zone to 1/10 the distance of ours. They'll live a really long time too, 1 trillion years or more. Imagine for the moment you built 100 such stars, maybe 100 a year away, each with its own smaller solar system or Dyson swarm. This is called a Kepler rosette, though we typically envision this as a ring of planets around a star, not a ring of stars. Each of the solar systems is only 50,000 light seconds, or just over half a light day away, so you can message them and get a reply back the next day. Many an empire of history operated fine with such communication lag times or bigger, so they don't have the problems of interstellar empires who have years of lag time and probably can't be very unified civilizations as a result. You could travel out there on a fusion drive or light beam, pushing the whole way at 1G and flip over and slow, and make it in just 29 days, achieving a maximum speed of 4% light speed. Amusingly, since these planets would tend to be tightly locked to their small suns, though you could probably make it so they weren't, their dark sides would still be decently lit by their neighbors, who would be just over 6 AU away, a little too dim for photosynthesis, but we could actually pack more suns into such a ring, or bring the ring in tighter and closer to home. We could also add other rings, cocked at different angles, same as we do with habitats around our own sun in making a Dyson sun swarm. How many can you pack in? Your limitation isn't really about mass, but waste heat. as it so often is in our discussion of these kind of topics. Build a sphere around the sun 100 AU out instead of the normal 1 AU, and you can have 10,000 times the brightness. And since those red dwarfs are only 1% as bright, you'd need 1,000,000 of them to have 10,000 times the brightness. An empire of 1,000,000 stars, all a day away to talk to and a month away to travel to. And you'd hardly have to stop there if you don't mind a little more signal lag and travel time. 1,000,000,000 stars if you don't mind a month getting a reply back and about half a year to travel there. You could pack 1,000,000,000,000 of these stars, a whole galaxy, into a region 100,000 AU in radius, not even half the distance to Proxima Centauri, though by this size, mass does begin to matter, and you notice time was running a bit slower in your galactic empire. Go much bigger, and your empire would turn into a massive black hole. It does give us a nice alternative to interstellar empires without needing faster-than-light travel. Such things are a long way off in our future, but do not violate any laws of science or require super technology to build, and like a normal Dyson swarm, can be made bigger incrementally as you need them. So, such empires are allowed in reality, not just in science fiction. This is no surprise. Reality is often much more interesting and stranger than fiction. We always try to look at the bright side of the future on this channel, and in this case, I suppose that's very literal. Our future is doubtless out among the stars, and we might be making them ourselves.
Since someone is bound to ask, while definitions in astronomy can be fairly loose, yes, suns is a plural term, and it's not our sun and the other stars. We say now a sun is a star that we've confirmed the existence of planets around, which is probably going to be almost all of them. This distinction matters because it's suns that are seen as offering us new lands to visit and make our homes. But of course that's not the only way. We've often discussed building our worlds and megastructures and Dyson spheres. Some would argue that name isn't actually appropriate, and that we should call them Stapleton spheres or swarms in honor of Olaf Stapleton, the philosopher and writer who first suggested the concept in his 1937 novel Star Maker, which along with his earlier novel Last and First Men, were the source of inspiration for so many of our classic science fiction novels written in the decades that follow. It's a bit of a standing joke that Star Maker is a very long book, not because it has many pages or is a tough read, but because you have to stop every few pages to think over some concept he laid out, and many ended up becoming their own entire novels written by another. The sheer depth and scale of Stapleton's works, in terms of concept and astronomical distances and times, is unmatched by any other writer, especially of his era. You can pick up a free copy of Star Maker today. Just use my link in this episode's description, audible.com/Isaac, or text Isaac to 500-500 to get a free book and a 30-day free trial. And that book is yours to keep, whether you stay on with Audible or not. And if you don't enjoy Star Maker, you can exchange it for another book, no questions asked. So today, as is often the case, we had our contemplations turned upward at the heavens. Next week, we'll go the opposite direction and explore the notion of civilizations going underground to ask why you might do it and how you could in subterranean cities. The week after that, we'll start our first look at some of the more peculiar or rogue civilizations the future might produce, as we explore the classic science fiction concept of space prison colonies. For alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share the episode with others. Until next time, thanks for watching and have a great week.